All right, today is July 7th, 2021. It's a Wednesday. Today we're going to discuss how supernova explosions are powerful, okay? And the explosive power in a supernova varies. Now, the type 1A supernovae, they are referred to as standard candles because their explosive power is between 1 to the 10 to the 44th power joules to 2 times 10 to the 44th power joules. That sounds very technical, okay? Another way to think of 10 to the 44th power joules is the amount of energy that our star will put out over its 10 billion life years. That's the total amount is equal to 1 times 10 to the 44th power joules is the same as the total amount of energy that our sun will put out over 10 billion years. Okay, now for a type 1A supernova, astrophysicists say that runaway carbon fusion, okay, instantly generates between 1 and 2, between 10 billion years and 20 billion years of power generation of our sun, okay? They say that that's done instantly through some sort of runaway fusion of carbon that isn't even carbon anymore, okay? Like diamond is carbon, but diamond doesn't burn, okay? So the white dwarf material, okay, that explodes when the mass of a white dwarf exceeds 1.40 solar masses, approaches 1.41 solar masses. When the mass of a white dwarf through accretion from a companion star, okay, when the mass approaches 1.41 solar masses, the white dwarf will explode in a supernova explosion. And that supernova explosion will have the explosive energy of all the energy that our sun puts out over its 10 billion year life. Or it could have twice that explosive energy. So all the energy that our sun could produce in 20 billion years, if he had a 20 billion year life, comes out instantly and blows the white nova apart, okay? The white dwarf, it blows it apart, okay? Now, the astrophysicists say that this is done with runaway fusion. Now, it's theoretically possible if, like, the entire mass of the white dwarf, which is at 200,000 times Earth density. So white dwarf matter is degenerated matter. It's not the same as carbon in the sun or carbon in a diamond, okay, or carbon, okay? It's like 333,000 times more dense than a diamond, okay? So this material in a white dwarf that's 333,000 times more dense than a diamond, it can't possibly fuse, okay? It's not possible. Okay, now we'll go to Sherlock Holmes, okay? He's got the answer for this. Sherlock Holmes. If you have eliminated all that is impossible, then whatever remains, however improbable, must be the truth. Arthur Conan Doyle, okay? He wrote Sherlock Holmes, okay? So we know what the astrophysicists say is impossible, okay? Even though it's theoretically possible, it can't happen because the stuff is 333,000 times. This carbon that they're talking about is 333,000 times more dense than diamonds, okay? So it cannot behave like a carbon gas or coal, you know. So, but we are given, physicists do give us, that if you mix 125 Earth masses, if you mix 125,000 Earth masses of matter with 125,000 Earth masses of antimatter, then you instantly get an explosion that's 1.5 10 to the 44th power joules. So we can explode. We are given a means to explode. Okay, we are given a means to explode. All we have to do is mix 125 Earth masses of antimatter, mix it with 125 Earth masses of matter, and away goes the white dwarf in all directions, okay? Now you ask, Adoni, how do you convert 125 masses of matter into antimatter? Well, it has to do with the spin, okay? If you look down on the North Pole, okay, protons, electrons, you can think of them as little dynamos, okay? They're little electric dynamos because they have a spin, okay? So because they have a spin and a proton is a dynamo, a proton sac is a proton permeable sac, is a dynamo because it has a spin. And because it's a dynamo, like the Earth and the Sun, it will have a North Pole and a South Pole, okay? Now, if we look down on the North Pole of a proton sac, a matter sac, it will turn clockwise. And if we look down on the North Pole of an antiproton, it will turn counterclockwise, okay? So relative to the spin, it'll either have a positive charge, like a proton, or it'll have a negative charge, like an electron. Now, if you look down on the North Pole of an electron, it will have the same spin as an antiproton, okay? Because the antiproton has a negative charge, and it's attracted to a proton. Okay, now we are given that protons and antiprotons are identical. The only difference is their charge. And the easiest way to change their charge is to change the spin relative to the North Pole. Okay? So the process of compression and decompression, a white dwarf cycles, and it cycles more and more. It compresses hard and decompresses, okay? Okay, now, when it expands out, a white dwarf, it doesn't, until the last explosion, it doesn't have enough antimatter to reach escape velocity, okay? So then it compresses again, and it creates more antimatter, and then it decompresses, and the antimatter, it mixes with matter and explodes. Now, once there's enough to reach escape velocity, then more antimatter is created because the pressure dropped. And then you get that antimatter mixing with the matter, and you end up with a total of 125 Earth masses of matter mixing with 125 Earth masses of antimatter, and you get a type 1a supernova explosion. Now, the other stars above that start with more than 9 solar masses of matter, okay? Now they'll leave a neutron star or a black hole. Now, and then they'll also make iron. So there'll be this iron dome. Okay. So the larger stars may require up to 1,250 Earth masses of antimatter to mix with 1,250 Earth masses of matter in the final compression and the final explosion. Okay, so the simplest way to understand is that compression, decompression of a star creates antimatter, and once there's enough antimatter, it reaches escape velocity, and away it goes. And a big star can make 1,250 solar masses of antimatter, and when that mixes with 1,250 Earth masses, 1,250 Earth masses of antimatter mixing with 1,250 Earth masses of matter, yields a big supernova explosion. Talk more later. Bye.